I'm Jared Pincus. I'm a rising senior at Stevens Institute of Technology, and in collaboration with Jordan Sucho of Stevens Cognition Lab, we've developed a novel procedure for empirically estimating the dimensionality of perceptual face space. Face space is a theory which describes the human comprehension of faces with a multi-dimensional geometry. Imagine a geometric space where people's faces lie at particular points, so that faces that are really similar lie in close proximity, and faces that are really different lie really far apart. Our research seeks to quantitatively estimate just how many dimensions face space tends to possess. Because face space isn't a concrete structure, we need to measure its properties indirectly. Here, we take advantage of an intrinsic property of geometric spaces that we call the nearest neighbor to average neighbor distance ratio, or ρ. To explain what ρ is, here's an example of its calculation. Suppose that you have some points in a geometric space, such that you can find the distances between each pair. Now make a table of all of these distances, noting for each point the distance to its closest neighbor and the average distance to all of its neighbors. Then compute the ratio of the minimum distance to the average distance for every point and take the average of those ratios. This is the value of ρ for this set of points. If we consider a random set of points sampled from some geometric space, the expected value of ρ depends on two variables: the number of points you sample and the dimensionality of the geometry. Here's a plot of the relationship between ρ and dimensionality, where the number of points sampled is fixed. As the number of dimensions increases, the expected distance ratio asymptotically approaches 1. Intuitively, a higher ratio means that random points in the space tend to lie further apart from each other. This is why we expect face space to have a small number of dimensions. Were this not the case, we would rarely perceive that people look alike. Since the relationship between ρ and dimensionality is bijective, we can take a ρ value for a set of points and back calculate the number of dimensions those points probably live in. This is the strategy our experiment uses for estimating the dimensionality of face space. Instead of random points, we consider random faces. And instead of measuring distance with some function, we have subjects measure the perceptual distance between faces. To randomly sample faces, we use the neural network StyleGAN, which allows us to generate artificial faces and interpolate between them. Shown here is a two-dimensional analogy for how sampling from StyleGAN's latent space works. You provide the network an input point, and an image depicting a face is generated. By interpolating from face to face, we can morph between them. We'll measure perceptual distance by the number of distinct identities a subject observes along the morph between two faces. For our experimental procedure, we begin by generating a random set of faces, then interpolating between each pair to create morphs. With these morphs created, we begin the procedure with the subject. Shown here is the experimental interface, which is all the subject sees during the trial. They're presented with two images at a time, and they're instructed to adjust the right image until the identities of the two faces are just noticeably different. Each time they decide that this JND has been reached, their position along the morph is noted and they're taken to another morph. A morph is completed once the subject notes a JND at or after the target image. Once the subject has completed all of the morphs, we count how many distinct identities they observed between each pair of faces. Just like the prior example with points, we can use these perceptual distances to compute the ρ value for this set of faces. From our pilot study using this procedure, the average ρ value among the conducted trials was approximately 0.76. Despite a small initial sample size, we found this fairly narrow 90% confidence interval. If we reintroduce the curve from before, which shows the expected value of ρ, we can create lower and upper bounds on our dimensionality estimate. From this, we find an estimate that face space has on average between 7 and 12 dimensions, which agrees with our hypothesis. If this result is accurate, face space possessing a mere handful of dimensions has some useful consequences. Further experimentation could enable us to disentangle the dimensions and determine the properties of each one individually. These results may also provide insight into dramatically simplifying artificial facial recognition technologies. While more testing is required to further refine and validate our results, this initial outcome is promising. If you want more details and commentary, check out our research poster. Thank you very much for your time and attention. Bye!